We are going to talk about 3 different properties today that trend in a particular way throughout the table. These are properties that the elements have. Now, atomic radius, I'm going to be just real clear. Atomic radius is how big the atom is, how much volume it takes up, how much space it takes up. It is technically the distance between the nucleus and the edge and the outer edge of the electron cloud, which would be your valence shell. So we're going to talk about what 2 things dictate atomic radius. Now, these 2 guiding principles will be what dictates the changes in all of the properties we discussed today. So, and those 2 things are energy shells and the positive charges in the nucleus. So the proton count and the number of energy shells that an element has dictates how large it is. So I'm going to show you guys how atoms are larger at the beginning of a period due to less protons. Now that will make sense more in just a second. An atom gets larger down a group due to an increasing number of energy shells. So let's take a look. Now, you can see that we have atomic radius increasing as we go from the right side of the table back over to the left. So basically backward across the period and then down a group. So we're going to explain why. So I'm going to just take a couple of sample elements to describe this. So first, if we take a look at sodium versus potassium, sodium has 1, 2, 3 energy shells, while potassium has 1, 2, 3, 4. So it would make sense that potassium is larger, okay, so you can see increasing atomic radius. It is larger because it has more energy shells. Plain and simple, it's because it has more shells. All right, and that goes for any 2 elements in the same group. So I could say nitrogen and phosphorus. Phosphorus has 3 energy shells. It's in period 3. Nitrogen only has 2, so phosphorus is bigger. So as we go down the periodic table, energy shells are increasing, and so the atomic radius or the size of the atom increases as well. Now, the other thing that we want to take a look at is what's happening across a period. So we see what's occurring as we go up and down the table. Energy shells, it affects the size of the atom. But what about when they have the same number of shells? So now I'm going to take a look at sodium and magnesium, okay? Sodium has 1, 2, 3 energy shells. It's in period 3. And magnesium has 1, 2, 3 energy shells. Now, based on the way I drew these, magnesium is slightly smaller. So it's like, well, why is it that magnesium is smaller? Why is it that as we go this way, that the size of an atom is increasing? Well, it has to do with the proton count, okay? So energy shells are changing through a group up and down the table, but as we go from left to right or right to left, the proton count is what is affecting the changes. So sodium has 12 protons in its nucleus, and magnesium has 12. Sodium only has 11. So basically, because sodium has less protons, only 11 protons at its center, and magnesium has 12, sodium is not able to pull in the electron shells, the energy shells, in as tightly. So let me put, just to make this a little more clear, let me use another element that's in period 3 other than magnesium. If you look, argon, which is down here at the end of the period, argon has 18 protons in its nucleus. So that means argon's nucleus is going to be much more powerful with 18 protons. So it's got more nuclear pull, meaning that the nucleus can draw those 3 shells in tighter and closer to the center than sodium can. So basically, as proton count is decreasing this way, the size of the atom is actually increasing. So less protons means less nuclear pull, which means that you can have the atom will get larger. Less proton count, or lower proton count I should have put there, means that you are going to have less nuclear pull towards the center, which means you end up being bigger, as is the case with sodium. All right, so less nuclear pull. All right, so two guiding principles. The proton count affects the size as it is lowering from right to left. Your atom gets bigger as you are going up. That is, if you're going from the top to the bottom of a group, the energy shells is increasing, which also makes the atom bigger. So essentially what you need to keep in mind is this. All right, this is just a real quick, good way to look at it, is that as you get closer to francium, okay, as you get closer to that bottom left-hand corner of the table, so right here is francium, all right, so you can think of there being a trend line, okay? As I go from this side, these are my smallest atoms. This is my biggest atom, okay? Why is francium the biggest? Well, it has a high number of energy shells with 7 energy shells, and then it also has a low proton count for its row, for its period, meaning it doesn't have as much nuclear pull, so it ends up being bigger. So atomic radius, the size of an atom, increases as we get closer to francium. Now, the next property we're going to look at is ionization energy. Now, ionization energy and the electronegativity, which we'll talk about after ionization energy, trend in a completely opposite direction than atomic radius. But it still is based on those two guiding principles, the energy shells, and the proton count. So we're going to take a look at this. So the ionization energy, okay, is the energy needed to remove, the amount of energy to remove an electron from an atom in its ground state. All right, don't put too much thought into this. Just think about it like this. So ionization energy, you can think of it like this. Think of a 6'4", 250-pound football player, and he's got his man purse, and then you've got this little old grandma that's like 85, and she's got her purse, okay? Who are you going to be able to rob easier? And you should say the grandma, in theory, right? In theory, it would be the grandma, all right, the little old lady, all right? And so there is less ionization energy needed to take her purse than, say, the big football player. It's going to require more energy. So on the table, we've got some that have lower ionization energy, easy to remove their electrons, and then higher ionization energy, harder to remove their electrons, which is going to be like the football player. So you got the grandma and you got the football player. Now, let's take a look at this. And this, again, it has to do with there is a period trend and a group trend based on the same guiding principles we talked about with atomic radius. So if you look here, you can see that ionization energy is increasing as we go to the top right corner. So like I said, completely opposite direction, but based on the same reasons, okay? So what this means is that as we go, and so I'm just going to select, so as we go from, say, lithium over to the opposite end of its period, lithium has a lower ionization energy than, say, neon, okay? Now here's why. The proton count. Yes, it still has to do with the proton count. So the thing is the higher the proton count, the stronger the nucleus. So over here you've got lithium. This is like your little old grandma. She's only got 3 protons, okay? You can think of proton counts as basically just dictating your strength, okay? Over here, neon's got 10 protons. This is your football player, okay? So ionization energy is the energy that an element's nucleus puts forth into holding on to its valence electrons. But this should make sense, okay? Seeing how when we think of, oh, who is it that is already stable and doesn't want to lose their valence electrons? These guys, okay? As you go across the table, we are going towards the noble gases, and they sure as heck are not going to give up their electrons easily because they're already stable and they want to stay that way, okay? So what we're going to take a look at now is what happens when we go up and down the group. So higher proton count, that pretty much makes sense. Not only that, but if you remember, these are our gainers, all right? They like to gain electrons. These guys over here like to lose. So naturally, we have a lower proton count, and we've got the elements that are going to lose, lose their electrons more easily. So low proton count means that there's going to be a lower ionization energy, a lower effort put forth into holding on to valence electrons. Over here, higher ionization energy, and it is due to that higher proton count, which makes the nucleus stronger. So again, this is when we were looking at a period. Now, let's look at that group trend, all right? Now, if you recall from when we were just looking at atomic radius, that the group trend is based on shells. So right here, if we look at the elements, let's say in the alkali metal family, all right, you've got lithium. All right, and it has 1, 2 shells, and then let's say we've got potassium that has 4 energy shells, okay? So remember, we just said that the reason why it's increasing, okay, has to do with energy shells, all right? But what about them? So this is where I like to share this analogy like with my daughter, okay? Let's say that I'm in Kroger and we're shopping and my daughter's next to me and we're in like aisle 2, and then all of a sudden she sees a friend from school, and that friend, and she's like, oh, hey, Hannah. And then she takes off and she goes with her friend. And she is now over on aisle 4 instead of aisle 2 where I am, okay? So follow me on this. In which case do I have more control and more protection that I can exhibit towards my daughter? And you should say when she's in aisle 2 right next to me. But if she's in aisle 4 away from me, I don't have as much control over her. I don't have as more protection. I don't have a greater means as to protect her if she's in aisle 4, not next to me. So this is where we look at lithium. Look at lithium and potassium both have 1 valence electron, okay? So they're in group 1, they have 1 valence electron. So I'm not drawing all the other electrons because right now they don't necessarily matter. So what we're looking at is lithium has 1 valence electron and potassium has 1 valence electron. Who's going to hold on to that 1 valence electron better? That would be lithium. Lithium is just like me when my daughter is right next to me, as opposed to potassium, whose valence electron is further away. The closer, okay, that valence electron is to the center of the atom, the nucleus, the greater energy you're going to have to put forth into taking it away, okay? So, again, what we're seeing is energy shells are dictating the change, okay? So as we go up the table, all right, as we're going up the table, the number of energy shells is lower, which allows our nucleus to have a higher ionization energy, a higher effort in holding on to its valence electrons, okay? So energy shells are, as these lower energy shells means more nuclear control, all right? Over here, as we go across the table, more protons means more nuclear power, okay? And so both of these things are allowing that ionization energy, that energy and effort in holding on to the valence electrons to increase, all right? So that's ionization energy. The last thing we're going to look at today is electronegativity. So this is another property. So we went over atomic radius, ionization energy, and now electronegativity. So if atomic radius is the size, and if ionization energy is the energy and effort that an element puts forth into holding on to its valence electrons, what is electronegativity? Electronegativity is literally how attractive an atom's nucleus is. How well an atom's ability to attract electrons from another atom, okay? So electronegativity increases from left to right. So it goes the same direction across the table, just like ionization energy, okay? But you need to know this. The noble gases are excluded from electronegativity. Not ionization energy, but they are not included in electronegativity. And you guys should be able to know why. Why is it that noble gases don't have an electronegativity value? Well, because they're not in the business of attracting electrons. They're already stable. Why would they need to attract electrons? So they are not included, and you'll need to remember that. They are not included in this property. Now, so electronegativity also increases as we go up a group. So it's going to be just like ionization energy. It's going to be based on those same principles that we just talked about, but for different reasons, different circumstances. So let's take a look. So don't worry about these shadow boxes, and do not worry about this. This was supposed to be omitted from this slide. But Electronegativity increases as we go up and over on the table. Notice that the noble gases are not included because they do not have a need to attract the electrons from other elements, okay? Now, so why is it that electronegativity, why are you more attractive? Why are you becoming more attractive as we go this way? Again, what we've already said today before is that proton count increases, okay? And what you need to understand is that as you go through a row, all right, so if we're comparing, say, sodium to chlorine, sodium has only 11 protons. Chlorine has 17 protons. Higher proton count just means a more attractive nucleus, okay? It attracts electrons better, all right? So it's just more attractive, all right? Now, and as we mentioned earlier, and the same sort of thing, as we go up the table, as we're going to the top of the periodic table, what is changing? We have less shells. Here, down here, there is 7 energy shells. Up here, we only have 1 energy shell, okay? So why is it that less shells makes you more attractive? So let's talk about that. So you have chlorine and fluorine. So I will let you know this, and don't ever forget it. Fluorine is the most attractive element on the periodic table, this guy right here, okay? Now, first of all, compared to the other elements in its row, we just said it has a higher proton count. That makes it more attractive. Fluorine has 9 positive charges. Lithium only has 3, okay? So we get it. More protons makes a nucleus stronger and more attractive, okay? But why is it that fluorine, which has less protons than chlorine, why is fluorine more attractive? We're seeing that it increases as we go up. Why is fluorine more attractive? Well, here we go. I always think this is funny to share this with students, okay? But it's a good analogy. It's a great analogy. It helps students to understand why fluorine's nucleus is more attractive. So let's take a look at these guys. I'm just going to fill in their electrons real quick, all right, because it's kind of important to understanding this. So both of these guys have 7 valence electrons. They have a attractive nucleus because they have high proton count, but one of their nucleus is more attractive than the other, and that's fluorine. So why is it that fluorine is the good-looking one, all right? Here's why. Think of it as in people, okay? I know these are atoms, but this really helps students to understand. If you have less layers, think of it as like clothes, okay? Fluorine has less clothes on, basically. Fluorine has less energy shells, okay? I know that sounds kind of silly, but you need to understand that fluorine, okay, has what we call more nuclear exposure. It has less electron shielding and more nuclear exposure, all right, because there's less energy shells covering up the nucleus. Here, this has what we call a greater amount of electron shielding, okay? So the electron shielding is higher. That is, the layers of electrons is higher. And so that makes it not as attractive, okay? So basically what I'm saying is that as you go up the periodic table, all right, as we go up, we have less shells, which makes the nucleus more exposed, making it more attractive, okay? So less energy shells, energy shells means that the nucleus is more exposed as we go up a group, which makes it more attractive, okay? So just remember that as you get closer to fluorine, then you are becoming a more attractive nucleus and have a greater ability to remove electrons from other atoms' electron clouds and basically steal them. Now, we're going to save Ionic Radius for tomorrow. And, yep, so we will pause with that today and then pick up with it tomorrow. All right, so Ionic Radius is not a directional trend like the ones we looked at yesterday. This is more of a like it's this or that. This trend has to do with whether it's a loser or a gainer, something that we talked about last week that we already talked about in terms of gaining and losing valence electrons, and it should make perfect sense, okay? So right here, cations okay? And this is a word for groups 1, 2, and 13. They are they are the elements of the groups that will lose their valence electrons in order to become chemically stable. Now, watch this. So if I take sodium, for example, sodium is in group 1, so it's one of our losers that loses its valence electrons, okay? Now, here's what sodium looks like in terms of its Bohr model. It's got 11 electrons. There's that one valence electron. This is what we call its normal, this is its Bohr model, okay? Well, you know how we had a electron configuration and then an ionic electron configuration? Well, you can also have an ionic Bohr model, and this is what's going to represent our ionic radius, all right? So right here, an ionic Bohr model is going to show our element once it has lost its valence electron. It is a cation. That's why it's got that positive right there. It's one positive because it now has less electrons and more protons, okay? So now when we draw sodium, okay, notice that it is now smaller because it lost that third valence shell, that third outer shell, and has a new valence shell. So this is sodium as an ion. So you can see that its original atomic radius, all right, here's its original atomic radius, and now here is its new ionic radius. So you can see that it is now smaller as an ion. So that's all you need to know. These guys right here are smaller as an ion, okay? And then the anions, which we'll take a look at one of those as well. An anion is going to be the opposite. We're going to see that they get larger. Now, the reason they get larger is a little different, okay? So it's not because they gain a shell, all right? So if we take the anions, they gain electrons due to increased electron repulsion. So I want to make sure we explain that. So let's take an element from group 15. Let's take the element nitrogen, okay? So nitrogen, this is going to be its original Bohr model, okay? So nitrogen has 1, 2, 3, 4, 5, 6, 7 total electrons, 5 valence electrons, okay? So they gain electrons in order to become stable. So this is the Bohr model of sodium. So this is just nitrogen rather. This is normal nitrogen, okay? Well, if I'm going to do an ionic model of nitrogen, we're going to show nitrogen with those 3 extra electrons that it has gained, okay? So this is going to be nitrogen, and I want to keep consistency, so let me change my color. All right, nitrogen. Now, and this should be a 3 negative charge right here since we're representing the ion. Notice that it is bigger as an ion.